So we talked a little bit last time about how to handle complex eigenvalues, and I just want to sort of put things into context because it looks like it was very complicated, but in fact it's really very simple when you get down to it. We go back to our old idea, and when I talk about our old idea, I mean back before the first exam. We were saying, okay, we were dealing with differential equations, and we had, there's a complex root showing up. And then we said, well, our solution should look like e to the alpha plus I beta t, which happens to break into real and imaginary parts. And then we said, hey, it turns out that we can grab the real part, and that's a solution, and we can grab the imaginary part, and that's a solution. Our new idea is say, do the same thing. So we have a complex eigenvalue. With it, there's a complex eigenvector. And just like as with the numbers, we can break it up into there's what we call the real part alpha and the imaginary part beta. We break up our vector into a real part A and an imaginary part B. So our solution, e to the eigenvalue t times eigenvector, which becomes this expression. And then we say, aha, same as before. We grab the real part and the imaginary part. The only thing that makes it extra interesting is to say, well, how do you grab the real part and the imaginary part is you have to do foiling. So the real part comes from multiplying the real part times the real part and the imaginary part times the imaginary part. That gives you the real part. And the imaginary part comes from the real part times the imaginary part and the imaginary part times the real part. And that's what gives you this piece. And that's it. That's the whole idea. So it shouldn't be too unusual. So let's do an example. Find the general solution for x prime equals 6 minus 2, 13 minus 4. All right. Well, let's see what happens. What's the first thing we should do when we see a problem like this? Starts with eigenvalues, yes. We can't find eigenvectors first. We always have to find eigenvalues first. Okay, so first step, remember we deal with an x prime equals matrix x, eigenvalues. Okay, so we're going to take our 6 minus lambda minus 2, 13 minus 4 minus lambda. Remember this is A minus lambda I, where A is our matrix. We take this determinant. All right, that becomes 6 minus lambda minus 4 minus lambda. Subtract 13 times negative 2. And we start expanding. That's minus 24 minus 6 lambda plus 4 lambda plus lambda squared plus 26. All right. Well, rewrite that. That becomes lambda squared minus 2 lambda plus 2. Because minus 6 plus 4 is minus 2. Minus 24 plus 26 is plus 2. And we set this equal to 0. All right. Solve for lambda. Well, it's not going to factor. In fact, you probably can guess we're going to get some complex roots because we were just talking about complex roots. It's a pretty safe guess. So how do we find those roots?
Quadratic formula.
You can use quadratic formula. And the other thing we can do? Complete the square. Which one do you want to do? Quadratic formula? All right, no worries. We can do it. So, quadratic formula, lambda is negative b plus minus square root b squared minus 4ac all over 2a. So that would be 2 times 1, I should say. All right, well, inside the square root, what do we have? So we have 4 minus 8, right? Negative 4. We take that square root, what do we end up with? 2i. So there's a 2i here. And there's a 2 here. And there's a 2 here. Very 2y. All the 2's cancel. What are we left with? 1 plus minus I. All right. Good. So, eigenvalues done. What comes next? Eigenvectors. Okay, so we have to pick 1 plus I or 1 minus I. Which one do you want? Yeah, do the plus. I always recommend the plus. Just because for what we're going to do next, the plus is the better choice. Not the eigenvector part, the part after that. Now, this might seem complicated, but hold on. Don't panic yet. 6 minus 1 plus I minus 2, 13, minus 4 minus 1 plus I. So I'm taking my a minus lambda I, clean it up. This would give us 5 minus I minus 2, 13 minus 5 minus I. All right? I think that's true. Now, what are we looking for? Well, we put on our hats and say, hey, when I'm looking for an eigenvector, I'm looking for something to put here. So when I multiply, I get 0, 0. The same thing is true, even though it doesn't look like it's true. Now, the thing that's true is that there's redundancy. These rows are multiples of each other. It's harder to detect when you have complex numbers because we're not really trained to see that so well. Which really means I just have to make sure I can multiply through to cancel off some row. So does anybody see a vector which can work?
0, 0.
Well, 0, 0 is a vector that definitely works, but it's not an eigenvector because the eigenvector can't be 0, 0. So someone said 2 and 5 minus I. Now you might say, whoa, where did that come from? Check this out. Check this out. See how this was 5 minus I and minus 2? You take these two numbers and you put them in reverse order. And then you change the sign on one of them. And you're done. Whoa, I know, like, what? That's it? Yeah, it works, guaranteed. You can check it out, right? You get 10 minus 2i minus 10 plus 2i equals 0. And then, this one might take a little bit of time to convince yourselves, but you have 26. And here, if you take minus 5 minus I and 5 minus I, multiply those together, you'd end up with negative 26. And so there we go. There's our eigenvector. Now, are we going to find our other eigenvector? No. We don't need it. It's not going to help us. We are going to start finishing up. We don't have much space left. So every bit of space is going to be needed. So here's the thought process. We say, let's write our answer like this. Okay, so in terms of the e and the cosine, using our 1 plus I, what do we get? What does that translate to here? E to the t, cosine t, plus I e to the t, sine t. Yes? The 1 plus I, I'm writing down the e to the 1 plus I t in its nice fancy way. Okay, so that's the 1 plus I. Now, I want to take this vector and write it as an a plus ib. So looking at this vector, what are the real parts of the entries? 2, 5. Okay. What are the imaginary parts of those entries? 0, minus 1. Okay, so we've now written this expression, this e to the lambda tv, but as real plus imaginary part, real plus imaginary part. So we can write down our answer in the space that remains. So x equals a. So a is our arbitrary constant here. We're going to grab the real parts. So we say, okay, we have e to the t cosine t times 2/5 and minus, because we have I squared, e to the t sine t 0 minus 1. Well, so we'll go ahead and write it as minus e to the t sine t 0 minus 1. That's our first function, plus b, and our second function, the imaginary parts. So e to the t cosine t 0 minus 1 and e to the t sine t 2/5. Are we done? Yeah, that's actually an answer. That's full points. Now, what's something we could do? Well, one thing you could do is we could actually combine these together if you wanted to in a single vector. So this is x equals a, and now we just combine. So you could say 2 e to the t cosine t, and then there's no sine t part because there's a 0, 5 e to the t cosine t plus e to the t sine t. Okay, so this is combine these two pieces together into a single vector. Plus b, same thing here. There's no e to the t cosine t, but there is a 2 e to the t sine t, and then a minus e to the t cosine t plus 5 e to the t sine t. So either one, either way to write it is full credit. All right, good. Whew. Nice. Any questions? There's a question.
Why didn't you need to find the other eigenvector again?
We don't need to find the other eigenvector because it comes from the splitting. Essentially what happens, we know what the other eigenvector is. The other eigenvector will be 2, 5 plus I. And then what happens is, it's not that this one thing becomes two things. It's that if you take this expression plus the conjugates, which happen because we know that things come in conjugate pairs, it's combining two solutions allows us to do our splitting. So essentially our other eigenvector helped us to split, but we didn't need to know what it was to do it. Other questions?
How does this work for a 3x3 situation?
Same processes, right? But as far as 3x3, so how do things look like for 3x3 complex? Everything works the same. You get a complex root. You only have one set of complex roots that come in pairs. You still find that eigenvector. Finding that eigenvector is more interesting. I don't know if I'm allowed to tell you this yet, but we will tell you at some point. Okay, I'll tell you now. God, you strong-armed me. I can't believe you do that to me. There will not be 3x3 matrices on the next exam. Everything is going to be, in terms of anything where you have to do an eigenvalue kind of thing, eigenvector, it's all 2x2s. So maybe does that help answer your question? Yeah. You still have to do homework. I should announce things like that more often. It's just like, wow. All right. So, with all that excitement behind us, a problem. Solve x prime, 7, 4, minus 10, minus 5x with x of 0 equals 10, negative 8. Similar process, but now an initial condition problem. Okay, let's talk about some milestones along the way. Is there a lambda, the eigenvalues? Do we know what those are? 1 plus minus 2i. Okay, good. Progress. Do we have an eigenvector for, let's do 1 plus 2i. What's the eigenvector? All right, so one person has suggested -4 over 6 minus 2i. Anybody else get that? Okay, I got that. Could you do anything to this eigenvector if you wanted to? Yeah. This is just one of them. You could also have said, oh, -2, 3 minus I. Now, oftentimes, I like to keep things as simple as possible, but not any simpler. Okay, great. So, our general form, x equals a. Can someone tell me what the first function looks like? e to the t cosine t. Oh, by the way, let's just note that this is -2, 3 plus I, 0, minus 1. So e to the t cosine t, oh, sorry, cosine 2t, excuse me, times -2, 3. And then there's an e to the t sine 2t, and that's going to be times 0, 1. Now you might say, ah, Steve, typo. That's supposed to be a -1. And I say, aha, double typo, because that should have been a minus there. And a minus makes a plus. What's the second part look like? e to the t cosine 2t times 0, -1. e to the t sine 2t times -2, 3. Okay, so there's the general form. Are we done? No. What comes next? Initial condition. So x of 0. A. When we plug 0 into this first function, what comes out? -2, 3. Everything else is gone. Plus b. What happens when we plug it in there? 0, -1. So note this is -2a on the top, 3a minus b on the bottom, and that's supposed to equal 10, -8. Can we use this to solve for a and b? So what is a? 2a equals -10, a equals -5. We know a equals -5. -15 subtract b equals -8. What is b? -7. So, final answer, -5, e to the t cosine 2t -2, 3 plus e to the t sine 2t 0, 1 -7 e to the t cosine 2t 0, -1 plus e to the t sine 2t. The hard part is just, it's a lot of copying. Okay, so that's it. Now, suppose we were like, well, I just want a single vector. One vector to rule them all. Can we do it? Yes. Okay, so let's do our top entries. How about e to the t cosine 2t's? What's going to be on the top entry? 10. e to the t cosine 2t. How about e to the t sine 2t's? Nothing there, and plus 14. All right, don't forget about that -7. Plus 14 e to the t sine of 2t. Downstairs, what's going to be in the e to the t cosine 2t? You have minus 15 here, plus 7 there. Together they give you minus 8. How about e to the t sine 2t? Here we have minus 5. Here we have minus 21. Together, minus 26. And there you go. Now you might notice like, ooh, these 10, negative 8 matches right here. Well, yeah, because what happens when you plug in 0? That goes away. So these coefficients do have to match that. Not a surprise. These, well, they're more interesting. All right, good. So you could do that, yes? Well, with more practice you can do that. You'll get some more practice. All right.
Are we expected to remember that for the last the formula for
So someone's trying to ask if we're expected to remember this formula.
Yeah. Sorry, that's what I was trying to say.
I don't memorize this formula because I have run out of brain cells. Too much deriving in my youth. I remember this formula. And I just remember, oh, grab the real part and grab the imaginary part. Because this is like, oh, e to the eigenvector t, e to the eigenvalue t, eigenvector, expand, grab the real part, grab the imaginary part. So I don't recommend you memorize this part. I memorize this part and how to get there. I think it's easier to memorize processes than it is to memorize formulas. Personal opinion. Personal opinion. All right. Well, okay. Switching gears. We'll move out of things which are complex. Okay, so verify that this matrix has these eigenvectors. So let's just do that really quickly. There's a punchline coming in just a few minutes, but you have to see it to see the punchline. All right. So how do you verify something, by the way? You plug it in. So we have 3 vectors here. Let's just take them in order. 7, minus 2, 4. All right, good practice for us. Minus 42, plus 14, plus 28. Together gives us 0. 14. Minus 6, minus 8 gives 0. Minus 28, plus 8, plus 20, 0. Is this an eigenvector? Yes. With what eigenvalue? What did you scale this vector by? So this vector times what gives you 0, 0, 0? Yeah, 0. So this is an eigenvalue of 0. So it's 0 times 7 minus 2, 4. Okay, so 0 is an eigenvalue. It didn't ask us for that, but it's part of the story coming up. All right, well, hopefully these other ones are just as fast. So we write this down again. 1, 0, 1. Okay, minus 6 plus 0 plus 7 gives 1. 2 plus 0 minus 2 gives us 0. Minus 4 plus 0 plus 5, 1. Is this an eigenvector? In other words, is 1, 0, 1 a multiple of 1, 0, 1? What multiple was it? 1. So this is an eigenvector for the eigenvalue 1. All right, one more. Once more to the breach, dear friends. Once more. Now we'll do 0, 1, 1. Okay, so 0 minus 7 plus 7 gives 0. 0 plus 3 minus 2 gives 0 plus 3 minus 2 gives 1. Minus 4 sorry, times 0 is 0. 0 minus 4 plus 5, 1. Is this an eigenvector? For what eigenvalue? 1. Okay, good. So this is a matrix which has lots of eigenvectors. Good news. Good news. All right. Switch gears. Find all the eigenvalues and eigenvectors for the matrix. 5, 4, minus 1, 1. Well, okay, we should get pretty good at this, right? Because it's going to be helpful for next week and for the week after that. And who knows? So, take our a minus lambda I, 5 minus lambda, 1 minus lambda, subtract negative 1 times 4. All right, well, that's 5. Then you have minus 5 lambda, minus lambda, and then a plus, well, and then there's a plus lambda squared and a plus 4. There we go. I forgot the lambda squared. If you put this all together, you get lambda squared minus 6 lambda plus 9. Does that factor? That's what? Lambda minus 3, lambda minus 3, lambda minus 3 squared equals 0. So we say, oh, lambda is an eigenvalue 2 times. All right. Cool, cool. We found all the eigenvalues. Now we're going to find all the eigenvectors. All of them. Every single one. Okay. So, we look at a minus lambda I. So that would be 2, 4, minus 1, minus 2. And the question is, what can you multiply that by and get 0, 0? So, sorry, what? Negative 2, 4? Negative 4, 2? 4, negative. Yeah, there's lots of people throwing answers at us. Okay, so I do think we can spot some pretty quickly. Like we have people say 4, negative 2. That'll work. 2, 4 won't work because that'll give us like, if you just multiply it, it'd be like 2 and 16. And that's like, hard to make that work. Okay, so that's one of them. Is there another one? Well, 0, 0 is out, right? 0, 0 is not an eigenvector, right? Rule of eigenvectors is it can't be 0, 0. 2, negative 1. Well, okay, but I'll add that to here. Any others? Negative 2, 1. Any others? Negative 4, 2. I mean, we're all dancing around it. We could also do things like 4 pi, negative 2 pi. I mean, there's all sorts of crazy things. But the real question is, okay, have we found lots of eigenvectors, or is it really just the same eigenvector? It's the same up to scaling. Is there any other vector that's an eigenvector that is not some multiple of this? And the answer is no. So here, this has only one eigenvector up to scale. So what's the issue here? What's the punchline? Well, the punchline is, how do we handle that? Now, you'll notice it's possible to have repeated eigenvalues and still come up with eigenvectors. That's why this example is here. And if you have the case that you have repeated eigenvalues, but you have enough eigenvectors, then, for instance, if we were looking at x prime equals ax in this case, we would say, oh, well, that's easy. It'd be something a e to the 0t, which just is 1, 7 minus 2, 4, plus b e to the t, 1, 0, 1, plus c e to the t, 0, 1, 1. So repeated eigenvalues are okay if we have enough eigenvectors. But when we have only one eigenvector, we say, well, great, x equals a. In our case, its eigenvalue is 3, so e to the 3t, and then we pick one of these, 2 minus 1, and then there's, of course, the question, what is going to go here? What's in the box? What's in the box? What is it? Well, the problem is we've got to do something. So that's the rest of today. So, dealing with the missing eigenvector. So it's not repeated eigenvalues that's the issue. It's a shortcut or missing, a shorting of these eigenvectors. So we're going to focus a lot on the 2 by 2 case, but this works in many general situations as well. And we say, all right, look, suppose we have a repeated eigenvalue. If you're missing an eigenvector, it has to be because you have a repeated eigenvalue, but not vice versa. So we have lambda are our eigenvalues. There's a single eigenvector. We know one solution. What's the other solution? Now we put on our hats and say, you know, we learned how to do stuff. Let's just do the same thing before. We say, okay, the thing we did before was multiplied by t. And we say, all right, does that work? And the answer is no. It fails. Now there's a couple reasons that are outlined. For one thing, the Wronskian is 0. And the Wronskian being 0 basically says you haven't done anything. These are not independent. But an even worse situation is it doesn't satisfy the differential equation. You say, well, you look at x prime. You have to use the product rule. So, you know, the derivative of e to the lambda t brings a lambda down. But then the derivative of t would just be 1. So that's our product rule. On the other hand, a times x is lambda t e to the lambda t v. And so we say, we've got to fix that part. That's somehow needs a correction. Now this is how a lot of math and science gets done. You make a guess. That's not bad. It's probably going to be wrong. I mean, that's what guesses are. But then you say, I have learned something. It wasn't completely wrong. I just have to make a correction. So you make a better guess. You say, all right, so we're going to have t e to the lambda t v plus e to the lambda t w for some w. Now, in order for this to work, we say, well, we need to make sure x prime equals ax. So we figure out what does x prime equal, and we carry out that computation. It's very similar to the one we just did. There's just an extra lambda e to the lambda tw. And we say, what does ax equal? We say, all right, we know that. And then we say, okay, the key is that these pieces on the end have to line up. So that tells us that AW minus lambda W has to equal V. Now, you might say, wait, what happened to all the e to the lambda t's? Well, what does happen to all the e to the lambda t's? Yeah, you divide out and they're gone. So if you set these two expressions equal, divide out by e to the lambda t, you come to the conclusion that AW minus lambda W equals V, or A minus lambda I W equals V. So we find that W, and that gives us our second guess. All right, so let's look at this. Find the general form for solutions. X prime equals 5, 4, minus 1, 1, x. We're not going to reinvent the wheel. We did the work. Half of it. We know what the eigenvalues are, so let's just copy. Lambda equals 3, 3. And we know what our eigenvector is. V equals 2 minus 1. So we join this problem halfway done. So our goal is figuring out how to finish it up. Say, all right, let's do that. So we're going to take A minus lambda I, and we write that down again. We've seen this before. We subtract 3 off the diagonal. 2, 4, minus 1, minus 2. And now, what are we after? Well, we're not after something times this equals 0, 0. We're after something where it equals 2 minus 1. So the question is, what does that? All right. So we'll call this A, B. So we need 2A plus 4B equals 2. Now, in case you're wondering where I'm seeing that from, I'm just carrying out the multiplication. So 2A, 4B. 2A plus 4B equals 2 minus A minus 2B equals minus 1. You notice anything about these two equations? They're the same, right? Which means there's redundancy, which is not surprising. There should be. So we need a choice for A and B, where 2A plus 4B equals 2. Now, I used the word A choice deliberately. There are many choices. We'll talk about that in a minute. I just need one. Does anybody see one choice which will work? Sorry, what? Well, if I put A equals 2 and B equals 0, that would be 2 times 2 plus 4 times 0. Does that equal 2? 1 and 0, right? 2 times 1 plus 4 times 0. So we say, aha, here's a choice for W. It would be 1, 0. And now we're like, well, great. That tells us our second guess. So we already said our first guess, well, not our second guess, our first function, a e to the lambda t, so in this case 3t, eigenvector. The second one will be e to the 3t, and now what it becomes is it's t times v plus our correction. So that's the solution. All right. This is best done with examples. We may not have time, because the other thing is there are other ways. So we're going to do this problem one more time.
Does this only happen when you have repeated roots?
This can only happen when you have repeated eigenvalues, but having repeated eigenvalues doesn't mean it will happen. So it always comes down to saying, look at the eigenvectors. If your eigenvalues are distinct, this will never happen. So, a few comments. The choice for W is not unique. However, what can it change by? The moral is it will only change by a multiple of V. And therefore, your second piece looks like W plus some multiple of V. And then you say, hey, this can actually be shoved into the first answer. So in other words, you can take this part and throw it into here. So why does that help us? Well, because there's an important lesson here. Be nice to yourself. Pick a simple W. Don't try to pick anything complex. Just be like, I'll pick the easiest thing I can. All right. Now, what you've just seen is what the book does. Here is what instructors like to do, giving you secret knowledge, which is to say, you know, the book says start at the bottom and work up. And we say, no, 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 no. Start at the top, work down. So how does it work? So here's what you do. If you go back to what you just saw here, do you see how you have a minus lambda I times W equals V? If you multiply both sides by a minus lambda I, and we'll do that really quickly, I hope, what happens to a minus lambda I times V? It's 0. So what you see is a minus lambda I squared W equals 0. Okay, so how does that help you? Say, all right, suppose you know that you have repeated eigenvalues and you're short in eigenvectors. So lambda equals 3, 3, and we know we came up short. And by the way, I will say, if you have a repeated eigenvalue for a 2 by 2 and it's interesting, you're missing an eigenvector. All right, so step 1. Find a minus lambda I squared. In this case, a minus lambda I, well, that's a matrix we've written down again and again. So we're going to square it. All right, let's carry out this computation. What's in the first entry? Zero. What's the next entry? 0. What's the next entry? 0. What's the next entry? 0. Okay, so we've now computed a minus lambda I squared. Step 2. Why am I using the same color? That's so unlike me. Step 2. We're going to take a minus lambda I squared times w equals 0, 0. So we're looking for some vector w. And we say, okay, there's 0, 0 times something gives us the 0 vector. Now, it can't be the 0 vector itself. So can you think of any vector such that when you multiply it by the 0 matrix, you get the 0 vector? Any vector at all, except the 0, 0. 1, 1, 1, 0, 5, 2, 107. Anything, as long as it's not 0, 0, works. And now we're like, aha, clever us, we found something. Now, if you had picked the exact same thing that we had before, you probably would wind back to the same answer. But it's okay. Answers can look slightly different. See, that's what this is saying. Answers can look slightly different depending upon how you make choices. And that's okay if your answers look slightly different. So now we're saying, great, we've done that. Let's finish this up, and then we'll call it a day. So the next thing is we've got to find our v. Well, how do we do that? Well, we take a minus lambda I times w. Oops, capital I. So that would be 2, 4, minus 1, minus 2 times 1, 1. What is that vector? Six. Negative 3. So there's our v and our w, and now our answer is x equals a e to the lambda t times v, 6, negative 3, plus b t e to the lambda t times v, plus our, well, here it'll just be w, 1, 1. So there you go. There's the other way to do it. All right, we'll stop here.